send neutrinos through the Earth. We bend them down by about 3 degrees, send them through the Earth, and they come out at the Sudan mine in northern Minnesota, where 2,400 feet or so underground, there is this type of object. The detector is there. It's about 8 meters high. So again, it's massive because neutrinos interact very little. The flux of them reaching a distant place is small. They are lucky to have this magnificent mural in their mine site. So this experiment has told us a great deal about the properties of neutrino oscillations. We make them here mostly as muon neutrinos. By the time they arrive there, some of them have changed into electron neutrinos or tau neutrinos. And this is really on the leading edge of neutrino physics today to understand these properties. A second newer experiment, also in northern Minnesota, is called the NOVA experiment. So here it is as it's being set up. It's also in operation now. This is on the surface. It's in a building that's as long as a football field, roughly. And you can see that the detector is about 4 stories tall. So these are big detectors in order to register what's happening at the other end. So just a few words about things that we've been doing that don't involve directly terrestrial accelerators. In 1941, Pierre Auger, who was one of the founders of cosmic ray physics, wrote a book translated into English with the title, What are Cosmic Rays? My colleagues are still asking this question, even though we've learned quite a lot in the intervening time. And the contribution of Fermilab and its collaborators to this subject has been to go from sort of cottage industry experiments to really big experiments. The really big experiment we have in mind is one that is actually conducted in Argentina. But if I put the apparatus, the array, center it on Fermilab, it looks like this. So it's a considerable installation. There's 1,600 ground stations and 5 stations that look up at the sky. Here you can see a cartoon of a cosmic ray, so a proton or something coming in from way out there, interacting in the top of the atmosphere, making a shower of stuff, lots of electrons and photons and so on, muons that come down to the bottom. Those are detected in the ground stations, but then you can also look up and see the air fluorescing as the burst of energy goes through it. So that's having 2 techniques to look at these things is one of the great features, in addition to the wide area that they cover in this case. Here is a Google Earth illustration. So you see a few houses over here being illuminated by muons and other things. And then the fluorescence detectors looking up and seeing a piece of track here, a piece of track there. And from that, they can reconstruct in 3 dimensions the trace of the cosmic rays and shower that came into their detector. So that's been a very productive experiment. One of the things that they've done is to measure the number of particles that reach us at stupendously high energy. At the energies they're considering, the rate of cosmic rays, primary cosmic rays, is about 1 per square kilometer per year, something like that. That's why you need a big detector and a lot of patience. And what they found is that as you go up above around 10 to the 19th electron volts, a little bit more, the flux of cosmic rays abruptly falls off. This was predicted because the universe at large is filled with cosmic microwave background radiation, the famous 3-degree radiation. And if it's really there, we know it's there, and protons of higher energy come along, they will hit the cosmic microwave background radiation and make pions by a process called photoproduction. And so there should be a cutoff at exactly this place in the spectrum. So that almost is a proof of the cutoff that's there as expected, but what remains to be shown is that there are actually sources of protons of energies higher than the cutoff would tell you. And that's the next step in the research. Another intriguing thing that they found is a change in the composition of cosmic rays. As you go up in energy, it looks like they're changing from protons to heavier nuclei as you go up. That's still work in progress and hasn't been sorted out. Anyway, the industrialization of that kind of research has really led to new insights. We've done some astronomical research. So the first is the Sloan Digital Sky Survey, and I just show you why it matters to be able to do big things. Here are 500 different supernovae observed in the Sky Survey. These are then followed up for study by the Hubble Space Telescope and other instruments. Here is a couple slices of the sky showing this filamentary structure in the stuff out there, the galaxies out there, again taken from the Sky Survey. And here is our most recent astronomical enterprise, the Dark Energy Survey in Chile. Here just one little illustration of what they've been doing. They and their colleagues have discovered some things called dwarf galaxies, which are satellites of our own galaxy, but are smaller and darker than the ones we knew about before. It's an illustration that our senses are limited, our instruments are limited. When we make improvements in our instruments, we discover new things. Here, by a technique using spectroscopic information, they're able to get rid of the foreground and to see the dwarf galaxy by itself. One nice little piece of work for them. Okay. So, two last things to talk about. One is our participation in the Large Hadron Collider at CERN. There have been two elements of this. One is to build pieces of the accelerator, in particular the magnets that bring the beams into small spots and give high collision rates. So a number of those are fabricated here at Fermilab by my colleagues. They look like big things, but they take a lot of meticulous work. The LHC, the Large Hadron Collider at CERN, is bigger than our machine. It's 27 kilometers around, or 17 miles around. The CERN laboratory is this little triangle. That's the LHC. It's about 100 meters underground. I always tell my friends from CERN, you know, they've got this nice little airport. We've got a much bigger airport. And they've got this cute little lake, and we've got a much bigger lake. They have the Alps. Anyway, there are two main experiments, and Fermilab is the United States headquarters for this CMS experiment, which lives over here. Their friendly rivals, the Atlas experiment, is here. And in this accelerator, which has about 7 times the energy of what our Tevatron had in its heyday, protons and protons collide head-on, and people have done great things, including, so here's the CMS detector that my colleagues participated in, big and brawny. It's 4 or 5 stories high, lots of steel and muscle, and also superbly fine electronics that you see here in the silicon tracker. This itself is about 4 meters in diameter. And these people, as you will recall from the 4th of July in 2012, together with their colleagues at the Atlas experiment, discovered the Higgs boson and gave us new insights into the nature of the origin of mass, the way that weak interactions work, and so on. And they have been involved in a new run of the accelerator at somewhat higher energy than 13 TeV. Just today, our CMS colleagues are switching out some of their sensor tracking apparatus for new and improved apparatus, and we expect more great news from them in the future. Okay, what's happening in Fermilab now and in the future? We're moving on with a suite of experiments. This is from the Microboon experiment, one of their first neutrino events in a new kind of detector for us to use for neutrino research. It's called a liquid argon time projection chamber. It serves in some respects as a prototype for what we hope will be the new gigantic experiments that we'll do in the future. And they're off to a running start. This gives pictures of bubble chamber aspect, but of much finer quality, telling you about the characteristic of the particles that are emitted and allowing you to say things quickly, electronically, and in great detail. So it's off to a great start. We're building muon experiments just behind us here. On the left, just behind the booster, you see the muon magnetic moment building. That's completed, and I'll show you something inside it. And then this is a somewhat old picture from last year. The building being completed next to it is for a new experiment that will look for an extremely rare, we think, disintegration of a muon into an electron, or transformation of a muon into an electron. Here is the magnetic ring for the muon magnetic moment experiment. This is a few months ago. They've done a lot of work in getting it ready for data taking. And maybe by the end of this year, or beginning of next year, they will begin taking data and give us answers after that. After that, the big deal that Fermilab has involved is to send neutrinos not just 500 miles to northern Minnesota through the Earth, but 800 miles to South Dakota, bustling village of Reed, South Dakota, where there will be very large underground particle detectors, and we hope to elaborate the mysteries of neutrino oscillations and other aspects of neutrino physics by doing that. So when I came here to Fermilab for the first time, I said a university, it was a great place.
ラクダのコブとラクダのコブが
I soon learned the most exciting place I could imagine being, and I'm hoping that it will be made for other young people the most exciting place to be. My colleague John Peoples, when he was director, liked to say that at Fermilab we make things and they work. And if you look at these pictures, I would amend his statement to say that our colleagues make very beautiful things and they work. Thank you very much. Also at 8 p.m. on Saturday, April 23rd. And I've been asked to mention we have a brand new lecture that's just been added to our calendar. That's on Wednesday, June 15th, special day. It's Barry Barish of Caltech, who will be here to talk about the recent discovery of gravitational waves by an experiment called LIGO. Hear that? Yeah, that's exciting. So his talk is entitled Einstein, Black Holes, and the Cosmic Chirp, which is a great title. So those tickets are actually on sale on our website now. The Arts and Lecture Series website is fnal.gov/culture. A couple other things I wanted to mention. If you have not been upstairs to our art gallery today to see the exhibit called Art of Darkness, that is all images from the Dark Energy Survey and of the observatory where that takes place, you really should. After the lecture, you're welcome to come upstairs and look at it, and the art gallery is open Monday through Friday, 8 a.m. to 4:30 p.m. if you want to come back. As some of you may know, we, in addition to all of the lectures and art series events that we put on here, sometimes we moonlight as a particle physics laboratory. We do science. It's pretty cool. We're always willing to answer questions about that. We have a new brochure that I would love to see you all take home, full of pictures and information. And we have a free public tour every Wednesday at 10:30 a.m. So on to tonight. I should mention tonight's lecture is completely sold out. We have a totally full flight. So thank you. Thank you all for being here. Very much appreciated. The speaker tonight is a professor of astronomy and astrophysics at the University of Chicago. He's a senior scientist at the Theoretical Astrophysics Group here at Fermilab. He got his PhD in physics from the University of Chicago. He's been at Fermilab since 1988. He was the head of the Theoretical Astrophysics Group from 1994 to 1999. He led the Sloan Digital Sky Survey Supernova Survey, which discovered more than 500 supernovae for cosmic study. And he is a founder and current director of the Dark Energy Survey. Ladies and gentlemen, Dr. Josh Freeman.
want to add my welcome to Fermilab, and where we'll be spending the next few hours talking about the dark universe. It's a big universe, lots to talk about. So to set the context, though, I want to start by reminding you of a few basic facts about the universe that I think everyone should know. So the first fact is that the universe is very old. Anyone know how old the universe is? 13.7. 13.7 billion. Good. All right, this is a good audience. Yeah. You've been reading ahead, or it's older than Bernie Sanders, either way. That's it for the political jokes for the night. So it's actually 13.8 billion years. It's gotten older. So how do we know it's old? Well, there are a number of things. It contains old things in it besides Bernie Sanders. The Earth, we know, is about 4.5 billion years old. The Sun, about 5 billion years. The oldest stars in our galaxy, about 13 billion years. And most recently, observations of cosmic microwave background that we'll talk a little bit about later have pinned it down to this 13.8 billion years. So this is just an example of some of the oldest stars in our galaxy. This is a globular star cluster, Omega Centaurus, an image taken by the dark energy camera that I'll be talking about later. Stars that are about 13 billion years old. Second basic fact about the universe, it's very big. I'm not going to ask how big it is, because it's really big. So the most distant objects we can see are about this many miles away. That's a lot of zeros. I think this is 100 zeta miles if you look it up. And of course, when we get to such large distances, miles are not a very good unit of distance. Too many zeros to keep track of. So instead, we use the fact that light travels very quickly, 186,000 miles per second. So in 1 year, light travels 6 trillion miles. So that defines a unit of distance, a light year. And so this many miles, that many zeros up there, corresponds to about 30 billion light years. So that's the most distant things we see are about 30 billion light years away. Just to set the scale, the Sun, our nearest star, is about 8 light minutes away. The nearest other stars near the Sun are a few light years away. So the universe is very big. Third basic fact is the universe contains billions of galaxies. So if you travel to the southern hemisphere, you have the advantage, if any of you have ever been down to the southern hemisphere, you go out on a dark night when it's clear, you can see galaxies with the naked eye. So just a little quiz. So this is a galaxy that you can actually see from the northern hemisphere. Anybody know what this galaxy is? Milky Way. Very good. All right. This is a very advanced audience. Great. Does anybody know what that galaxy is? Wow. Right. Small Magellanic Cloud. That's right. This is the large Magellanic Cloud. These are two dwarf galaxy satellites of the Milky Way. You can only see them from the southern hemisphere, not from the north. So if you ever do go down south, I urge you to go out on a dark night and see these quite spectacular. So these are examples of nearby galaxies, and the universe is filled with billions of these galaxies. This is a more typical galaxy, and they're typically about 60,000 light years across. Contain tens of billions of stars, and they rotate like this galaxy, like our own Milky Way, rotates around its center with on an average, it takes about 200 million years to complete one rotation. This is also an image taken with our camera. So if we can bring the maybe lights down just a little bit, I want to show you a few examples of some pretty galaxies that we've taken pictures of with the dark energy camera. This is NGC 253. I'm sure you all knew that. In the constellation Sculptor. And this is, of course, the familiar NGC 1560. These galaxies are a few tens of millions of light years away. So galaxies, there are billions of them. They're all around the universe, but they don't exist in isolation. They live in and are shaped by a variety of environments and proximity to other galaxies with which they occasionally interact. Sort of like my teenage daughters occasionally interact with me. Galaxies occasionally interact with others. Sometimes you find them in pairs or in groups or in clusters of tens to hundreds of thousands of galaxies. And those in themselves form part of a larger cosmic web of structure. We used to call these superclusters. So this is just an example here I pulled out. NGC 1672 is a nice large spiral galaxy in the foreground. But if you look down below here, you see a number of more distant, therefore they look smaller galaxies in a group of galaxies. And this is sort of the first hint that these galaxies are not just randomly distributed throughout space. They cluster together. Here's NGC 1703 in the foreground, but if we look a little closer, and if you look on the right of that galaxy, again you see a lot of these smaller yellowish galaxies. That's a more distant cluster of galaxies that you see behind this foreground. So galaxies clump together here, and clusters of galaxies. This is a cluster of galaxies. Another image taken from the Dark Energy Survey. Again, all those yellowish galaxies are all in a relatively small volume of space, that being a few million light years across, and they cluster together. This is a very famous cluster of galaxies. This isn't an image from our survey. The Coma cluster of galaxies. And again, clusters are sort of the largest gravitationally bound systems we know of in the universe. Again, a few million light years across. And they contain about 1 quadrillion times the mass of the Sun, 1,000 trillion times the mass of our Sun.